Hello, I'm Louise Dennis. I am today at the University of Liverpool, but as of tomorrow, I will be at the University of Manchester. So I've put both my email addresses up on the slide. I'm going to talk about some joint work that I've done with Rafael Cardozo, who is a postdoctoral researcher on the robotics and AI for nuclear hub for robotics in extreme environments, and two project students that I had last year at Liverpool. And I'm going to talk about ethical governance systems viewed as a multi-agent problem. So an ethical governance system is something which sits on top of an autonomous AI system and controls its actions to be in accordance with some ethical system. So the first ethical governance system we're aware of was by Arkin, and it was for a weapons targeting system. And the idea was that we would constrain the targets selected by the underlying system so that they were in accordance with the laws of war and the rules of engagement. So you can see some images from his paper here. Here is one of the constraints, and that is prohibiting the selection of targets which are of cultural significance, such as churches or art galleries and things like this. And this is a visualization of the underlying targeting system that is selecting a particular location to target and flagging up various buildings and vehicles that are in the proximity of that target, which then might be relevant to the reasoning about ethics. And his system is divided into two components, what he calls the evidential reasoner. That's this system here, which is flagging up the kinds of things that might be hit by the release of the missile, and the arbiter, and that's what reasons with these constraint-based systems. And this case, it would veto any systems that were deemed, any targets that were deemed unethical. It also has a second phase where it tries to tweak the exact targeting process to minimize the amount of collateral damage. So the example we were looking at is a very simple simulation of a human, that's this H here, in a workplace together with a robot. Now the human is wanting to go around the workplace and complete various tasks, and they are in these squares marked G. G is for goal. So the human, we have a very simple simulation of human. They walk around these goals in order, performing their task. However, the workplace has a number of hazards in it, and that's these H's here. And we were envisaging these being radiation hazards, specifically some kind of low-level radiation hazard. So we don't want the human to get too much exposure to the radiation, but it's not fatal if the human steps in one of these squares with a radiation hazard in it. And what we were interested in was when the robot is trying to do two things at once. It wants to keep the human safe, and it can do that by getting in the human's way and standing in a hazard to prevent the human walking into the hazard. But we also wanted to respect human autonomy. So if the human is wearing adequate protective equipment, knows what they're doing, has assessed the risk, then the robot should not be getting in their way too much. They should not be annoying the human. And this is not just because we want the human to be able to do what they want to do, but also we know that if computational systems become too irritating, people start finding ways around them and they cease to be effective. Now, this example was based upon an example in a paper by Alan Winfield. In this example, this H robot is modeling a human, and it is wandering around oblivious to the fact that there is a hole in the ground that it might fall into. This is the robot in the space, and it uses simulation techniques to predict when the human's path will take it towards the hole, and then it moves in the way of the human to prevent it getting there. One of the things we were interested in is if you're thinking about safety, then in this kind of workplace environment, simulation is an obvious way to try and assess whether the human is going to get into danger or not. But if you're thinking about some other values, such as privacy, then you might want to do a very different sort of reasoning. And here we have an example from a master's thesis which is trying to reason about whether some action taken by an AI system will preserve privacy. And this is using a lot of logic-based reasoning with an ontology and policies. So something that looks much more like traditional AI reasoning than the simulation that's being used here. But if you had a complex AI system trying to reason about ethics, then it might want to take various different sorts of reasoning involved. So a proposal from myself and Michael Fisher was that instead of having a single evidential reasoner as you have in Arkin's system, you should have multiple evidential reasoners. Each of these reasoners would assess the situation specific to the value they were interested in, and then they would send information about that to some kind of ethical arbiter. So we imagine there could be a safety reasoner that's reasoning using simulation, a privacy reasoner, which is reasoning according to some policies, and a variety of others, perhaps even reasoners which aren't explicitly about ethics. So you can imagine having a politeness reasoner, which is about obeying social norms. For instance, how close a robot should stand to a person in order to respect their personal space. All of these submit information to an ethical arbiter that uses some ethical theory to decide between their competing claims and then veto or suggest actions to the underlying autonomous system. So the idea that Thomas and Daniel came up with was to represent each of these reasoners as a rational agent. Now, rational agents are often called beliefs, desires, intentions agents, and their programs are controlled by selecting actions based on the goals of the agent and its current beliefs about the world. Now, I've shown a few fragments of the agent code here. Obviously, there's quite a bit of syntax, so I don't want to go through it in all its gory detail, but for instance, this is a fragment of the code in the safety reasoner, which is reasoning about whether the human is currently safe in the space. So its current goal is to check on the human and see if it needs to do anything. If it believes the human is in danger and it believes it's not currently standing in front of the human, then it will move towards the humans. And it sends a recommendation to the arbiter agent. And in this case, these numbers, the first number indicates which particular action it's chosen. So 11 corresponds to move toward, and then the 3 is a utility value saying how important it thinks it is that it intervenes in this particular situation. Here we have the human autonomy reasoner, which is trying not to get in the human's way too often. And this one's goal is if it's to check on the human and it's not currently in the way of the human, and the human currently isn't near danger, that's what near one means in this context, but the human has already been annoyed, then it will recommend that the robot doesn't move, and it sends this choice to the arbiter, again, with a value of 3. So in this particular situation, we're doing utilitarian style reasoning. We want to know which is the option which has the highest utility. What the arbiter does is it has some multiplier for autonomy and safety, which dictates how it weighs the importance of the recommendations from these two reasoners. So it multiplies the scores supplied by the two reasoners, and if the safety score is higher than the autonomy score, then it chooses the proposal that's come from the safety reasoner. Otherwise, it chooses the proposal that has come from the autonomy reasoner. So although this is a utilitarian style system, one of the benefits of using a rational agent is that we could actually have something that looks more like, for instance, deontic logic style rules inside the arbiter, and therefore it could reason in terms of obligations and prohibitions. For instance, if the safety reasoner said the human was in very great danger, then maybe it's always obliged to pick the safety reasoner's choice, irrespective of what the autonomy reasoner is saying. So we then, in that simple environment we showed you, ran some simulations, because one of our hypotheses is that ethical reasoning in even moderately complex environments, you will end up with a lot of rules and special cases and things you want to consider, and then it becomes quite difficult to understand whether you've really captured the ethics you want. So one of our claims here is that if you have these reasoners and arbiters that express what they're doing in terms of beliefs and goals, then you can tweak various parameters, run simulations, and it's fairly clear what's going on. So for instance, here in this table, A is the scaling factor we have applied to the autonomy reasoner, and S is the scaling factor we've applied to the safety reasoner. So if you look at this line here, then you can see here we're scaling the safety reasoner by 3, so it's quite a bit higher than the autonomy reasoner. And in this case, the number of hazards the human steps on is only 1, compared to it stepping in 3 hazards in all other cases. But we can see the number of times that the robot has blocked the human's 49, which is higher than in all the other cases. Interestingly, the human actually achieves more goals in this situation, and we think that is to do with the avoidance behavior with the human is actually just on this particular map bizarrely more optimal than the human's default reasoning about how many goals it could go around. And we can see that it's chosen, and over 200 runs, it's chosen the safety of reasoners' advice every single time and never chosen the autonomy reasoners' advice. But we can see in some of the other runs, for instance here, if autonomy's scaling factor is only a little bit higher than safety, then the number of times that it actually blocks the human is a lot lower, and it actually makes relatively little difference in terms of the hazards and goals to a number of other settings, and autonomy is getting chosen a number of times over safety. I think it's important to stress at this point that we don't think this simulation is particularly realistic. So we're not learning useful things about this particular case, how you should weight autonomy and safety in a genuine nuclear scenario. One of the things we'd be hoping to do is take some of the data and simulations that are coming out of the Robotics and AI for Nuclear Hub research, where they've got robots mapping storage facilities for low-level radioactive waste, and then rerunning much more realistic simulations to see if we can imagine if a robot and a human are doing some kind of joint inspection task in this space, the robot can be allowing the human to get on with their job while making sure the human doesn't accidentally get too high a dose of radiation. But these particular results we don't think are particularly convincing. We just wanted to show that in principle, this framework allows you to see what the ethics are that you've encoded and how you've encoded them, and then also run some simulations to make sure that the outcomes of that encoding are as you anticipated. Thank you.